In this video, we will be analyzing a simplified MS2 graph to determine a peptide sequence. In order to create an MS2 graph, the mass spectrometer is analyzing individual peaks from an MS1 graph. Each peak is a peptide segment from a whole protein and needs to be analyzed further to determine the individual amino acids in the sequence. MS2 graphs are complicated in real life, which is why computers are used to aid in the statistical analysis. To understand what a computer is doing, we are going to look at how to analyze a simplified MS2 graph to determine the amino acid sequence of a peptide chain. Here is a simplified MS2 graph. We will be analyzing this graph in this video. Extra background noise was removed from the graph to focus on the main peaks. Each peak represents a peptide fragment, where each peak is characterized by MZ and intensity values. In real MZ graphs, we have mass to charge ratio, which is MZ. For simplicity, we converted the MZ to mass to simplify the calculations. Notice there are 4 peaks associated with the B ion, and 4 peaks associated with the Y ion. This helps determine the number of amino acids in the sequence. The number of amino acids in the sequence is the number of peaks for a single ion plus 1. In this simplified case, that means that there are 5 amino acids in this peptide chain. While this is not always true depending on modifications like phosphorylation, in our simplified graphs, we will assume that this is true.
To determine the amino acids in the sequence, we need to remember the direction each ion represents in the peptide chain. Since the B ion is associated with the N-terminal of the amino acid, the B ion represents the beginning of the peptide chain. Conversely, the Y ion is associated with the C-terminal of the amino acids and therefore represents the end of the peptide chain. This means that when we are reading a B ion peak, we are working our way from the beginning to the end of the peptide chain. Similarly, when we are reading the Y ion peak, we are working our way from the ending of the peptide chain to the beginning. So, let's start to determine the peptide chain sequence. We always want to start with the peaks with the lowest mass value. Remember, the height of the peaks do not mean much at this stage, but what is important is the mass value. These values are recorded above each peak in our simplified graphs. The reason we start with the smallest peaks is that we can assume that these are single amino acids. Larger mass values are more likely to be a combination of amino acids, so we want to start with the smaller values and build to interpret more complex values in sequences.
The first peak here is a B ion, which means we are looking at the beginning of the peptide chain. The mass value for this peak is 101.1051. This number is proportional to the mass of the amino acid or acids represented by this peak. Therefore, we can look for this number in the chart of amino acid masses. The amino acid with this mass is threonine, or T. Therefore, the first amino acid in our sequence is T.
The second peak is a Y ion. This means that it will be the last amino acid in our sequence. The mass value is 128.1742 and is proportional to the mass of lysine, K. Therefore, the last amino acid in our sequence is K.
Next, we are going to need to start analyzing peaks with larger mass values. This means that there may be multiple potential combinations of amino acids. However, since we already know 2 of the amino acids, we can use this information to determine the next amino acids in the sequence. The next smallest mass peak is a B ion. Since the mass value of this peak does not match any amino acid masses, we can assume that there are 2 amino acids represented by this peak. We already know one of these amino acids is threonine from the previous B ion peak, and we know the total mass of the two amino acids together. So the mass of threonine and the unknown amino acid must equal 238.2463. If we isolate the unknown amino acid by subtracting the mass of threonine, we can determine that the mass of this amino acid is 137.1412. Looking at the amino acid mass chart, this amino acid must be histidine, or H.
A similar process can be completed for the next Y ion peak. However, this time we are working with the C terminal of the peptide chain, or the end of the amino acid sequence. Since the mass value doesn't correspond to any amino acid mass value, we can assume that this peak contains two amino acids. One of those amino acids must be lysine, K. This means the sum of the mass of lysine and the unknown amino acid must equal 242.2781. By subtracting the mass of lysine, the mass of the unknown amino acid is 114.1039. Looking at the amino acid mass chart, this corresponds to asparagine, N.
The peak with the next smallest mass value is a B ion. We can assume that this peak includes 3 amino acids. The first 2 amino acids we know are threonine, T, and histidine, H. We know that the mass of these amino acids is 238.2463 from the previous B ion peak. Therefore, the sum of the mass of these amino acids and the unknown amino acid must equal 351.4058. By subtracting, we can determine that the mass of the unknown amino acid is 113.1595.
Looking at the amino acid mass chart, there are two amino acids with this mass, leucine or isoleucine. A more complicated analysis would need to be completed to determine which is present. For now, we will just say both, since we can't distinguish between the two amino acids.
Since we know all the amino acids, we can check our work with the next Y ion. By summing the last 3 amino acids in the sequence, the total should be the same as this next Y ion peak. So, by adding the mass of isoleucine or leucine, asparagine, and lysine, we get a total mass value of 355.4376. This is the same as the mass value of our next Y ion peak. Therefore, we have determined the sequence accurately. Our peptide sequence is T, H, I, or L, N, K. If we wanted to be more thorough, we could continue to check our work by examining the last 2 peaks to determine if the masses are the same for the expected number of amino acids.
This video was created by Carly Hankey, recorded by Carly Hankey and Alex Choi. This video was funded by the National Science Foundation. Any opinions, findings, or conclusions expressed in this video are those of the creator and do not necessarily reflect the views of the National Science Foundation. A special thank you to Dr. So-Young Ryu and the Ryu Computational Laboratory Group for providing feedback and support for the content and recording of this video.